Now we'll study multiple summations and we'll focus mostly on double summation. So we'll study multiple summation. Now, multiple summation we are going to introduce here. We are to learn a few models, basically what it is, how to think about it, and how to solve problems. But it'll come in its full force when we study binomial theorem. In binomial theorem playlist, you'll find multiple summations covered. Now, the first thing is, what is a double sum? Now, we know that a single sum is sum of all elements in a sequence. Suppose summation ai. So this is a1 plus a2 plus an. Now, when we say a double sum, we express it as this summation. Say I varies from 1 to n, j varies from 1 to n, aij. Now, before solving any double summation, first we should understand the region and the points. So we need to understand the region from which we have to choose the values of I and j. Now, since both I and j, they can take the values from 1 to n. So we'll form a rectangular grid. So I will be your row and j will be your column. So j will take the value 1, 2, 3 up to n. And I'll also take the value from 1 to n. And then we have this first element a11, a12, a13 to a1n, a21, a22, a23, a2n. And here will be this an1, an2 and ann. So basically we have n square points. So we are taking the summation over those n square points. So basically this aij double summation is nothing but it is sum of all the elements in this grid. Now this grid, it need not be a square. It can be any rectangular grid. Say for example, we have to find the summation. I varies from 1 to 3. J varies from 1 to 2. I plus j. Now this, if we look at the region, this I, it takes 3 values, 1, 2, 3. And j, it takes only 2 values, 1 and 2. So there will be total 6 elements. Now each element is I plus j. So if we add 1 plus 1, this is 2. 1 plus 2, 3. 2 plus 1, 3. 2 plus 2, 4. 3 plus 1, 4. 3 plus 2, 5. So we just need to add all these elements. So this is 5, 5, 10, 18, 21. So this double summation I plus j is nothing but sum of all these elements along the grid, which comes out to be 21. Now for a square grid, these elements, they are along your diagonal. So along the diagonal, the elements will have I equals j. Now in this lower triangle, you'll have all the elements where I is greater than j, and in the upper triangle, you'll have all the elements where I is less than j. Now in multiple summations, the single most important classification is independent versus dependent indices. So one of the classification is independent versus dependent indices. Now, independent indices are the one in which the inner index does not involve the outer index. Say, for example, this summation. Summation I varies from 1 to m. Summation j varies from 1 to n. A ij. So basically, it's a grid over m cross n rectangle. And this j, it runs from 1 to n, regardless the value of I. Now, in this independent indices, if we have a term which can be factorized separately, say aij, it can be factorized as bi and cj, then we can split this double summation. I varies from 1 to n, j varies from 1 to n, aij. This double summation I varies from 1 to m. So here this is m, and j varies from 1 to n bi into cj, and we can write this as this summation I varies from 1 to m bi into this summation j varies from 1 to n cj. Suppose we want to find out this double summation I varies from 1 to 3, j varies from 1 to 4, 2i into 3j. Now indices are independent and this term is already factorized. So we can write this as this summation I varies from 1 to 3, 2i, and this j varies from 1 to 4, 3j. Now this is 2 and this is summation I. This is n plus 1 by 2, and this is 3 into summation j. So this again is n plus 1 by 2. So this 4 will cancel. So this double summation, it is simply 360. So in independent indices, we are talking about whole rectangular region. But in case of dependent indices, say for example, we have this summation I varies from 1 to n, and this summation j varies from 1 to I, aij. Now in this j, it does not run from 1 to n. Instead, this j, it runs from 1 to I. So its upper limit is I. Now in order to process this, we have to understand which lattice points on the grid we are talking about. If we have this n cross n grid, so this is A11, A12, A1n, A21, A22, A2n, and AN1, AN2, ANN. Now we are taking the first one as I, so this is I, and this is j. Now the points on the diagonal, they'll give us I equals j. Now points below the diagonal will give us I greater than j, and point above the diagonal will give us I less than j. Now suppose we have to choose I is greater than or equal to j, then what we'll do is we'll choose the points in the lower triangle along with these diagonal elements. In case of dependent indices, we have to look for the lattice points which we're going to use in our summation. Now basically here, this double summation, it is equivalent to this double sum aij, where j is less than equal to I and it is less than or equal to n. This is an equivalent notation of writing this same double summation. And when we have dependent indices, then it is not a rectangular region, it is a triangle. Now we take a very simple example. Suppose we are given this double summation. I varies from 1 to n. J varies from 1 to ij. Now basically in double summation order matters. So when we are writing this, it is actually this. So first we have to calculate this inner sum, then we have to calculate this outer sum. Now this is summation j from 1 to I. So it will be nothing but this summation I varies from 1 to n, and this is n plus 1 by 2, or this is simply 1 by 2 summation I square plus I, where I varies from 1 to n. Now this is 1 by 2 into summation I square plus 1 by 2 into summation I. Now this is 1 by 2 and summation I square is n plus 1 to n plus 1 by 6, and this is 1 by 2 n plus 1 by 2. Now you can simplify and solve it. So basically every double summation Aij, it can be expressed as a single summation Aij, where we need to choose the lattice points Aij from a region R, and this region R is the allowed region. So if the indices are independent, then this region R will be a rectangular grid, and if they are dependent, then it will be the lattice points inside a triangle. So whenever you are solving a double summation, do not see sigma first, see the region. So once you can identify the region, then the problem becomes simple. Find triple summation. I varies from 1 to infinite, j varies from 1 to infinite, k varies from 1 to infinite, 1 upon a to the power I plus j plus k. So I can actually express it as I varies from 1 to infinite, j varies from 1 to infinite, and k varies from 1 to infinite, 1 upon a to the power I into 1 upon a to the power j into 1 upon a to the power k. So it is a case of multiple summation when the variables are independent. So what I'll simply do is, I'll simply express it as summation I varies from 1 to infinite, 1 upon a to the power I into j varies from 1 to infinite, 1 upon a to the power j into summation k varies from 1 to infinite, 1 upon a to the power k. Now each of the series is nothing but a geometric progression. So it is 1 upon a plus 1 upon a square plus 1 upon a cube up to infinite. And since mod of a is greater than 1, then 1 upon mod a is less than 1. So this infinite geometric progression, it converges, and its sum is a, which is 1 upon a upon 1 minus r, which again is 1 upon a. So if I'll simplify, I'll get this result as 1 upon a minus 1. So this first one will be 1 upon a minus 1. Second one, it will also be a minus 1. And the third one, 1 upon a minus 1. So answer to this question is a minus 1 to the power minus 3. Now the question is, find the value of this sum, which is this summation k varies from 1 to infinite. This sum n varies from 1 to infinite k upon 2 to the power of n plus k. Now here the variables are independent, so we can write k varies from 1 to infinite k upon 2 to the power k into this summation n varies from 1 to infinite 1 upon 2 to the power n. Now this is an AGP and this is a simple GP. If we solve this GP, it is 1 by 2. 1 by 2 square, it is an infinite GP. First term is 1 by 2. Common ratio is also 1 by 2. So value of this summation is simply 1. And if we solve this AGP, this sum, it is 1 upon 2, 2 upon 2 square, 3 upon 2 cube, and we write s by 2 as 1 upon 2 square, 2 upon 2 cube, and we subtract, we'll get s by 2, and this is 1 by 2 plus 1 by 2 square plus 1 by 2 cube, which again is a GP whose sum is 1. So value of this sum is simply 2, and that's your option D. Now here this first question is we need to find some of this series, which is summation r varies from 1 to n, summation s varies from 1 to n, delta rs, and this is 2 to the power r into 3 to the power s, where delta rs is 0 if r is unequal to s, and this is 1 if r is equal to s. So though it's a double summation problem, the problem is very simple. So when r and s, they are different, this entire term will be 0. So we'll only have non-zero terms when r equals s. So that means this s, it will be, when r is 1 and s is 1, it will be 2 into 3. When r is 2, s is 2, there will be 2 square into 3 square, 2 cube into 3 cube, and continue up to 2 to the power n into 3 to the power n. It is nothing but just another way of writing a GP. So this is another notation in which we can write a GP. So this s is nothing but a GP, which is 6 square, 6 cube up to 6 to the power n, which is a r to the power n minus 1 upon r minus 1, and that is the answer to this question. Now for this second part, it says we need to find this triple sum I varies from 1 to n, j varies from 1 to I, and k varies from 1 to j, and this is 1. Now first we'll solve this. Now this is 1 plus 1 plus 1, j times, so it will be this summation I varies from 1 to n, and this is summation j varies from 1 to I, and this is j. Now summation j is I into I plus 1 by 2, so we can write this as this summation I varies from 1 to n, I into I plus 1 by 2, or this is this summation I square plus summation I divided by 2. Now summation I square is n plus 1, 2n plus 1 by 6, and summation I is n into n plus 1 by 2. Now what we'll do is we'll take n plus 1 by 6 common. We can write this as n plus 1 by 12, and here we'll have 2n plus 1, and here will be simply 3. So this is n plus 1, and this is 2n plus 4, which is 2 into n plus 2 upon 12, which we can also write as n plus 1, n plus 2 divided by 6, and that is the answer to this question. Now the question is, we need to simplify this summation, which is r varies from 1 to n, summation r square minus summation m varies from 1 to n, summation r varies from 1 to m, summation r. Now first we simplify the summation r. We can write summation r varies from 1 to n r square minus, and this is summation m varies from 1 to n, and this is m plus 1 by 2. So basically this is summation r varies from 1 to n r square minus, and it is 1 by 2, summation m varies from 1 to n m square minus 1 by 2, summation m varies from 1 to n summation m. Now limit of summation goes to 1 to n. Then this variable, it doesn't matter. So what we'll do is, rather than taking it as m, we'll write it as r. So we can write simply summation r varies from 1 to n r square minus 1 by 2 summation r square, r varies from 1 to n minus 1 by 2 summation r varies from 1 to n. Now this is 1 by 2 r square. So we can write this as 1 by 2 and then it'll be simply summation r square, r varies from 1 to n minus summation r varies from 1 to n, and that's your option C. Let us take up a question, and here the question is, we need to solve this double summation. I varies from 1 to n, j varies from 1 to n, minimum of ij. Now what we'll assume is, we'll say for a fixed number I, we can write this summation j varies from 1 to n, minimum ij, it will be j when j varies from 1 to I. Because in that case, j will be minimum, and plus from I plus 1 to n, it'll be simply I. Now this is sum of first I numbers. So it'll be this I plus 1 by 2. And here summation is in j, not I. So this is just constant. So it'll be simply I into, and number of terms will be n minus I. So this is your first part, and then we'll take summation over I. So this summation I varies from 1 to n, summation j varies from 1 to n, minimum of ij will be this summation of I over 1 to n, I square plus I by 2 plus in minus I square, which will be this summation I varies from 1 to n, 2n plus 1 by 2I, and then minus I square by 2. Now if we solve this summation, it'll be 2n plus 1 by 2, and summation I is n plus 1 by 2, and here it'll be this 1 by 2 n plus 1, 2n plus 1 by 6. So it'll be this 12, and we'll take n plus 1, 2n plus 1 common. It'll be 3 minus 1, 2. So we can write this as n plus 1, 2n plus 1 divided by 6. Now there could be double summation problems where we have this model where I is less than j. So suppose we have this condition that 1 is less than equal to I, it is less than j, and it is less than equal to n. Now we have to choose the region inside this rectangular grid. So this is your I and this is your j. So I can take the values 1, 2, 3 up to n, and similarly j can take the values 1, 2, 3 up to n, and this is a11, a12, a1n, a21, a22, a2n, and an1, an2, and ann. Now if we count all the points in this rectangular grid, we know we have total n square points. Now number of points in diagonal, it will be n. So in the diagonal, we'll have n points. Total, it'll have n square points. Now, how many points are remaining? So the remaining points are n square minus n. And since we have two triangles, so in each there'll be n square minus n by 2 points. So there'll be n square minus n by 2 points, or simply NC2 points. So if we have this summation I is less than j is less than equal to n, and this 1, now this is not a summation problem, it's just a counting problem. And we know that in this, since I is less than j, we are talking about this upper triangle, and number of elements in this upper triangle is simply NC2, or n minus 1 by 2. Now let's take another example. Another example is this summation I is less than j, it is less than equal to n, and this is I plus j. Now we can write this as this summation j varies from 1 to n, and this I, it varies from 1 to j minus 1 I plus j. Now first we'll solve this inner summation. So it'll be this summation j varies from 1 to n, and this is summation I varies from 1 to j minus 1 I plus this summation I varies from 1 to j minus 1 j. Now this is this summation j varies from 1 to n. Now this is simply summation r. So it will be n plus 1 by 2. So it will be j minus 1 j by 2, and plus, now this j is constant because index here is I. So it will be simply j into j minus 1. So it will be this summation j varies from 1 to n 3 by 2 j square minus j. Now we can write this as this 3 by 2 summation j square minus summation j. Now this is 3 by 2 summation r square is n plus 1 2n plus 1 by 6 minus, and summation j is n plus 1 by 2. Now if we take n plus 1 by 2 common, we'll get 3n plus 1 by 4, and here will be 2n plus 1 by 3 minus 1. So it will be this 3n plus 1, and this is 2n minus 2, so 2 into n minus 1 upon 12. So this is n square minus 1 by 2. Then another model is when I is less than or equal to j. In this, we are going to add diagonal elements along with lower triangle. So basically, if we have this model where I is less than equal to j, aij, it is nothing but this summation I is less than j, aij, which is lower triangle, plus sum of diagonal elements where I is equal to j. So in general, we know that this summation j varies from 1 to n and I varies from 1 to n, aij, it is equal to this summation when I is less than j, aij, plus sum of diagonal elements, aij, and plus sum of upper triangle elements. So we can split this rectangular summation in these three parts, and depending on the region, we can choose the appropriate summation. So we have done this question, which was you have to find this summation 1 where I is less than j and is less than equal to n. So here we have chosen all the elements which were in lower triangle, and we know that this is equal to nc2, which is n minus 1 by 2. But if we take this equality sign, then we can write 1 is less than equal to I, is less than equal to j, is less than equal to n, 1. Now this region, it also includes diagonal element. So it will be this nc2 plus n. So it will be n plus 1 by 2. So it's just a counting problem. Now for counting, we already know this summation. I is less than j, is less than equal to n. Summation 1, this is nc2. If we have 3 variables, so I is less than j, is less than k, is less than equal to n, it'll be nc3. And if we have this summation 1 less than equal to I1 less than I2 less than IR is less than equal to n, 1, then it will be simply NCR. So let us take up another problem in triple summation, and that is triple sum of 1 when I is greater than equal to 0, j is greater than I, k is greater than j, and k is less than or equal to n. So I'll write it as summation. Now this value of k, it should be greater than j, so it'll start with j plus 1 and it'll go all the way up to n. Now value of j, it is greater than I, so it'll start with I plus 1, and the maximum value it'll have is j should be less than k, so here it'll be n minus 1, and the minimum value of I, it'll be 0, and its maximum value should be less than maximum value of j, and it should be n minus 2, and we need to find this triple sum of 1. Now if I'll find this summation 1, so I can write it as summation I varies from 0 to n minus 2, j varies from I plus 1 to n minus 1, and here it will be 1 plus 1 plus 1, so number of summation times, and there will be n minus j plus 1 plus 1, so that should be summation I varies from 0 to n minus 2, j varies from I plus 1 to n minus 1, and it should be n minus j. I can also express it as summation I varies from 0 to n minus 2, j varies from I plus 1 to n minus 1, and then I'll write it as n minus j c1, because I know nc1 is simply n. So if I'll put the value of j, I can write the series as summation I varies from 0 to n minus 2, and then if I'll put j as I plus 1, I'll get n minus I minus 1 c1, n minus I minus 2 c1, n minus I minus 3 c1, and we'll continue. So last value of j will be n minus 1, so there will be 1 c1. So before that I'll have 3 c1 plus 2 c1 and plus 1 c1. So that's my series. So what I'll do is I'll replace this 1 c1, because I know 1 c1 is simply 1. So I'll replace 1 c1 with 2 c2. So ncn is simply 1. So if I'll use the property n same and r differs by 1, so it'll be 3c2. Now 3c1 plus 3c2, there'll be 4c2. So in the same way, if I'll solve the series, then I'll write the series as summation value of I varies from 0 to n minus 2, and here it will be, the last one should be n minus I minus 1 plus 1, and then c2. So minus 1 and plus 1 will cancel. I'll get the series as summation I varies from 0 to n minus 2, and that should be n minus I c2. Now I'll try and solve this series. Now for this series, I'll write it as, so if I'll put I as 0, I'll get it as nc2. Then for I as 1, n minus 1 c2, n minus 2 c2, and then finally when I put I as n minus 2, I'll get it as 2c2. So I'll write 4c2 plus 3c2 and plus 2C2. Now again NCN is 1. So I'll write 2C2 as 3C3 because for both of them the value is 1. So if I'll use the property again here, n is same, r differs by 1. So then it will be 4C3. Now 4C2 plus 4C3 will be 5C3. So if I'll continue in this fashion, then finally I'll get n plus 1 C3. So the answer to this triple summation is n plus 1 C3. So now let us take another question in multiple summation, and the question is summation of summation of summation of summation of 1, and we need to prove that it is nc4 plus twice nc3 plus nc2 where I is greater than equal to 1, j is greater than equal to I, k is greater than j, w is greater than equal to k, and less than or equal to n. So I'll split the summation. So I'll write it as summation. Now this w, it starts with k and it goes all the way up to n. Now this k is in fact greater than j. So k starts with j plus 1 and it goes all the way up to n because there is an equality sign here. Now this j is greater than equal to I. So this j starts with I and it is less than n. So it will go to n minus 1 and this value of I, it will start with 1 and again it will go to n minus 1. And we need to find sum of this series. Now first I'll find this sum. So this sum is sum of 1 plus 1 plus 1 from k to n. So that should be summation n minus k plus 1. So I can also express it as triple sum of n minus k plus 1 c1 because I know that nc1 is same as n, and here the value of k varies from j plus 1 to n. So I'll simplify this summation. So I'll write it as double sum where I varies from 1 to n minus 1, j varies from I to n minus 1, and here the first value of k will be j plus 1. So if I'll put k as j plus 1, so 1 and 1 will cancel. I'll get n minus j c1 and then n minus j minus 1 c1, and finally if I put k as n, I'll get this as 1 c1. So here I'll get 3 c1 plus 2 c1 plus 1 c1. Now what I'll do is, I know that 1 c1 is 1 and so is 2 c2. 2 c2 is also 1. So I'll use the binomial coefficient property, in which is if n is same and r differs by 1, it is n plus 1 cr. So I'll write it as 3c2. Now 3c1 plus 3c2, again n same, r differs by 1. So that should be 4c2. So if I continue in this fashion, I can write it as summation I varies from 1 to n minus 1, j varies from 1 to n minus 1, and here it will be n minus j plus 1 c2. So if I'll simplify the series, I'll get this result as n minus j plus 1 c2. Now I'll start expanding in terms of j. So I'll write it as summation I varies from 1 to n minus 1. So I'll put the value of j as I. So here I'll get n minus I plus 1 c2. If I'll put j as I plus 1, then I'll get n minus I c2. I'll continue up to, so if I'll put j as n minus 1, so here n and n will cancel. So here I'll get 2c2. So I'll continue up to 2c2. So I'll get 4c2 plus 3c2 and plus 2c2. Now again, what I know is 2c2 is simply 1 and so is 3c3. So I'll replace 2c2 with 3c3. Now 3c3 plus 3c2, so there'll be 4c3. 4c3 plus 4c2, there'll be 5c3. So if I'll continue in this fashion, I can write it as summation I varies from 1 to n minus 1. And here if I'll add one more, I'll write n minus I plus 2, and that should be c3. So it changes to n minus I plus 2 c3. So now I'll expand this series. So now if I'll put I as 1, I'll get it as n plus 1 c3, then n c3, n minus 1 c3, and finally If I put I as n minus 1, so I'll get it as 3c3. So I'll write 5c3 plus 4c3 plus 3c3. Now now 3c3 is again 1. So I'll replace it with 4c4. Now n same, r differs by 1. So there'll be 5c4. Now again n same, r differs by 1, 6c4. So finally in the end, I'll get n plus 2 c4. So answer to this summation is n plus 2 c4. Now if I look at the series on the right hand side, so on the right hand side, I have this expression which is nc4 plus 2 times nc3 plus nc2. So I'll write it as nc4 plus nc3 plus nc3 plus nc2. So now n same, r differs by 1. So I'll write n plus 1 c4, and here will be n plus 1 c3. Now here again n is same and r differs by 1. So there'll be n plus 2 c4. So the series on the left hand side is n plus 2 c4, and the series on the right hand side is also n plus 2 c4. So this is how we prove this given result. Now one of the classic example in double summations is symmetric products. So they'll ask you to evaluate this summation xi into xj, and they'll say this I is less than j and is less than equal to n but greater than equal to 1. Now this, what we do is we start with squares of the sum. So we'll take this xi where I varies from 1 to n whole square. Now we know that x1 plus x2 plus xn square is x1 square plus x2 square plus xn square. So it'll be this summation xi square where I varies from 1 to n, and this is nothing but sum of diagonal elements plus 2 x1 x2 plus x2 x3 plus x3 x4. So it'll be this 2 times this summation 1 is less than equal to I is less than j less than equal to n xi into xj. So this is sum of product of terms taken 2 at a time. So this is sum of product of terms taken 2 at a time. So such questions, they'll become this identity. So I is less than j equal to n, xi into xj will be 1 by 2 summation xi whole square minus summation xi square. And in this, if we have equality also, so suppose we want to find this xi xj, and this is 1, I is less than equal to j is less than equal to n. So it will be this sum plus sum of diagonal elements. So it will be this 1 by 2 sigma xi square minus sigma of xi square and plus sum of diagonal elements, which is simply sigma xi square. So it will be this 1 by 2 sigma xi whole square plus sigma xi square. So once you know the region, then you can figure out what needs to be done. If we take an example, suppose we have to find this sum, which is this summation 1 is less than equal to I is less than j is less than equal to n, I into j. So we know that it'll be equal to 1 by 2 and then summation I square minus summation of I square. Now this is 1 by 2 and this is n plus 1 by 2 whole square, and this is n plus 1 to n plus 1 whole divided by 6. And if the same question is this summation ij and I is less than equal to j less than equal to n, then it will be this 1 by 2 n plus 1 by 2 whole square plus n plus 1 2n plus 1 by 6. Now the question is sum of product of 10 numbers taking 2 at a time is. So we have these 10 numbers 1 plus 2 plus 3 plus 5 and then minus 1 minus 2 up to minus 5, and what we'll do is we'll take their whole square. Now it'll be 1 square plus 2 square plus 3 square up to plus 5 square plus again 1 square 2 square up to 5 square. So it'll be this 2 times 1 square plus 2 square up to 5 square, and then it will be plus 2 times sum of products of these 10 numbers taken 2 at a time. So it will be this summation ai into aj, where say I is less than j. And this is the required sum. So we need to find this sum and say this sum is s. Now left hand side is 0 and this is 2 times and this is n plus 1 to n plus 1 whole divided by 6 plus 2s. Now this 2 will cancel, this 6 will also cancel. So value of s is simply minus 55, and that's your option B. Now here the question is, let A1, A2, An be terms of GP whose common ratio is R, and let Sk denote sum of first k terms of the GP. Then value of this sum I is greater than equal to 1, less than j, that is less than equal to m, ai into aj. Now this is sum of product of terms taken 2 at a time. Taken 2 at a time. Now it says if there are n quantities in GP with common ratios R. So we have this GP whose suppose A, AR, AR square and A R to the power n minus 1. And if SM denotes the sum of first m terms. So this SM, it is A plus AR plus AR square up to AR to the power m minus 1. Then it says that show that the sum of product of these m terms taken 2 at a time is this value. Now we know that this SM, it is A 1 minus R to the power m upon 1 minus R. Now if we square both sides, we can write A plus AR plus AR square up to AR to the power m minus 1 whole square, and it is equal to A square and then 1 minus R to the power m square upon 1 minus R whole square. Now we can write this as A square plus AR whole square, AR square whole square plus AR to the power m minus 1 square plus 2 times, then it will be AB, AC, AD, BC, CD. That is, it will be sum of product of these m terms taken 2 at a time, which is what we need to find in this question. Let us say this is a required sum S, and this is equal to A square into 1 minus R to the power m whole square upon 1 minus R square. Now this again, it is a GP whose first term is A square and common ratio is R square and number of terms is m. So it will be this A square 1 minus R square to the power m upon 1 minus R square plus 2s, and that will be equal to A square 1 minus r to the power m whole square upon 1 minus r square. Now we'll take this on right hand side. We can write 2s equals a square 1 minus r to the power m whole square upon 1 minus r square minus, and this is a square, and we can write this as a plus b into a minus b. So we'll write 1 plus r to the power m into 1 minus r to the power m upon, and this is also a plus b into a minus b. So it will be this 1 plus r into 1 minus r. Now what we'll do is we'll take a square 1 minus r to the power m upon 1 minus r common. So we can write 2s equals a square 1 minus r to the power m upon 1 minus r, and then what you're left with is 1 minus r to the power m upon 1 minus r minus 1 plus r to the power m upon 1 plus r. Now this a into 1 minus r to the power m upon 1 minus r, it is nothing but sum of m terms, which is Sm. So we can write 2s will be equal to a into Sm, and here we can write this as 1 minus r into 1 plus r, and here will be this 1 plus r minus r to the power m minus r to the power m plus 1, and here will be this minus 1 minus r to the power m plus r to the power m plus 1. Now here this 1 will cancel and r to the power m plus 1 will also cancel. So we can write this as 2s equals a sm, and here we'll take 2 common and we'll also take r common, and there will be 1 minus r to the power m minus 1 upon 1 plus r into 1 minus r. Now this a 1 minus r to the power m minus 1 upon 1 minus r, it is nothing but it is s m minus 1, and this 2 and 2 will cancel. So we'll get this s as sm into this sm minus 1, and then we also have this r upon 1 plus r, which is what we need to prove in this question. Now, just like summation problems, we can use techniques in double summations also. So we can use telescopic sum. Say, for example, we have this double summation. I varies from 1 to n. This j varies from 1 to I. 1 upon j minus 1 upon j plus 1. So first we have to solve this inner product, which is nothing but telescopic sum. So it will be this summation. I varies from 1 to n, and here will be this 1 minus 1 upon I plus 1. Now if we take this sum, it will be this summation 1 minus this summation 1 upon I plus 1, where I varies from 1 to n. Now this is n minus, now this is 1 by 2, 1 by 3, 1 by n plus 1. So this is hn plus 1, but we do not have first term. So it will be hn plus 1 minus 1. So this double summation will be n plus 1 minus hn plus 1, which is your harmonic sum. Now the second technique is interchanging the order of summation. So we know that I varies from 1 to n summation j varies from 1 to I aij. It is basically a looped summation. So this is j varies from 1 to I aij, and then this summation of I. Now, if we have to interchange the order of summation, then it will be this summation j varies from 1 to n, and then this summation I varies from j to n aij. And basically this is nothing but this is counting the lattice points. So for same ij, this I, it won't be from 1 to j, it'll be from j to n, because we are taking the same elements from the same region. For example, if you're given this summation I varies from 1 to n and summation j varies from 1 to I j, we can write this as this summation j varies from 1 to n, and then this summation I, it varies from j to n j. Now in this summation, index is I and variable is j, so which is basically constant. So it will be this summation j varies from 1 to n, and it will be j into, and number of terms in this will be n plus 1 minus j. Now we can simplify this as n plus 1 into summation j minus summation j square. So if we have to interchange the order of summation, then you'll have to remember, if j goes from 1 to I, then I will start from j and go to n. Now for independent finite indices, the order does not matter. So if we have this summation I varies from 1 to m, summation j varies from 1 to n aij, it'll be same as this summation j varies from 1 to n, summation I varies from 1 to m aij, because we are talking about the same lattice points. So either we add them row wise first or column wise first, it doesn't make a difference. The end result will be you are adding all the points on the rectangular grid, only the root changes. So far we have studied so many techniques to solve. So we have studied AP, GP, HP, AGP. Then we have also studied summation formulas. Then we have studied telescopic sum and ratios. We have also studied reverse summation, where we have reversed the series to find the sum. Then we have studied difference technique, where we just subtract the series to find nth term, or shifting and multiplying with R to solve GP and AGP type problems. Now, no lecture can actually cover all the models, but once you have enough clarity and depth with understanding of how things work, you can figure things out, and you can use different techniques and combinations on your own to engineer a solution. So I'll name a few more techniques that we may use. One technique is pairing. Now in this, what we do is we pair two or more terms such that our series, it becomes simple. Say for example, we are given the series, find the summation k varies from 1 to n fk upon fk plus f n plus 1 minus k. Now basically this is reverse summation, right? So we can write this as this summation k varies from 1 to n. Now we can replace k with n minus k plus 1 or n plus 1 minus k. So it will be this f n plus 1 minus k upon f n plus 1 minus k plus fk. Now if we add them, we'll get 2s, and then this summation k varies from 1 to n. Now here it'll be fk plus fn plus 1 minus k upon fk plus fn plus 1 minus k, which is simply 1. So solve the series simply n by 2. So this reverse summation is also an example of pairing. Another example could be this series. This summation k varies from 1 to 89, 1 upon 1 plus 10 cube k degrees. Now here n is 89. Now n plus 1 minus k will be simply 90 minus k, and we know that 10 90 minus k will be simply cot k degrees or 1 upon 10 k degrees. So we can write this series as this summation k varies from 1 to 89, 1 upon, and this is 1 plus, now this is 10 90 minus k, cot k will be 1 upon 10 cube k degrees or 10 cube k upon 1 plus 10 cube k. Now again if we add, we get 2s equals this summation k varies from 1 to 89. Now this is 1 plus 10 cube k degrees upon 1 plus 10 cube k degrees, which is 1. So it will be simply 89. So this sum will be simply 89 by 2. So again in this we have used reverse summation, or what we could have done is, we know that we are given 1 upon 1 plus 10 cube k. Now it is of the form 1 upon 1 plus t. Now if we take 1 plus 1 upon t, then it'll be 1 upon 1 plus t plus t upon 1 plus t. It'll be 1. We know that for 10 1 degree, we can write 10 89 degree as cot 1 degree, which is 1 upon 10 1 degree. So if this is t, then this is 1 by t. So here for 1 and 89, this sum will be 1. For 2 degrees and 88 degrees, it'll be 1. So we have these pairs from 1 to 44, for which we'll have a corresponding 1 upon t. So this sum will be 44, plus then we have this term when the value of k is 45, and we know that 10 45 is 1. So it'll be 1 upon 1 plus 1, 1 by 2. So it'll be simply 44 plus 1 by 2 or 89 by 2. So previously we have solved it using reversing technique. Now we have solved it using pairing. So we are pairing the terms so that each pair, it gives us a constant term. Then we have our obvious methods such as rationalizing, method of difference, using integration and differentiation, standard power sums. Then for telescopic, we often use partial fraction decompositions. Another common technique which is used in sequence and series is using symmetry or pairing or grouping. So we can use pairing, grouping, and symmetry. Now, say for example, we need to find this summation. R varies from 1 to 99, R upon 100 minus R. Now, what we can do is, we can write this as summation R varies from 1 to 99 and R minus 100 plus 100 upon 100 minus R. So it will be this summation R varies from 1 to 99 minus 1 plus 100 upon 100 minus r. Now this summation minus 1 is minus 99 and plus 100 into this summation r varies from 1 to 99, 1 upon 100 minus r. Now if we expand this, we can see that it'll be this 1 by 99, 1 by 98, 1 by 97, 1 by 2 and 1, which is your 99th harmonic series. So we can write this as minus 99 plus 100 H99. So basically what we have done is we have paired this R with R minus 100 and plus 100. So there are so many techniques and models that we cannot simply cover, but if we understand how and why things work, then we have enough tools to attack any problem. Now here the question is, we are given this function fx, which is 2 to the power x upon 2 to the power x plus root 2, and we need to find this summation r varies from 1 to 2n minus 1, 2 times f r by 2n. Now what we'll do is we'll write f r by 2n, and there will be 2 to the power r by 2n upon 2 to the power r by 2n plus 2 to the power 1 by 2, and we'll also write f1 minus r by 2n, and there will be 2 to the power 1 minus r by 2n upon 2 to the power 1 minus r by 2n plus 2 to the power 1 by 2, which we can write as 2 upon 2 plus 2 to the power 1 by 2 into 2 to the power r by 2n. Now we'll cancel root 2, so we can write this as root 2 upon root 2 plus 2 to the power of r by 2n. Now if we add these two, we can write f r by 2n plus f1 minus r by 2n. It will be equal to, and the numerator will have 2 to the power r by 2n plus root 2, and in the denominator also we will have 2 to the power r by 2n plus root 2. So this value, it is equal to 1. So we have established this relation that f r by 2n plus f 1 minus r by 2n, it must be equal to 1. Now if we look at this series will be f 1 by 2n plus f 2 by 2n up to f 2n minus 1 by 2n, and this is basically f 1 minus 1 upon 2n. And then we have this 2 here, so what we'll do is we'll write the series again, but now we'll reverse it. So we'll write 1 minus 1 upon 2n. Next one will be f 1 minus 2 upon 2n, and in the end we'll have f 1 upon 2n. Now if we add all these pairs, value of each of the pair is 1. So how many pairs do we have? We have 2n minus 1 pairs. So value of this sum will be simply 2n minus 1. And that is the answer to this question. Now the question is, we are given the series Sn, which is this summation k varies from 1 to 4n minus 1 k plus 1 by 2 into k square. Now if we write first few terms, we can write this Sn as Now if we take k as 1, we get this is minus 1 square, and then if we take k as 2, it will be minus 2 square. For k equals 3, it will be plus 3 square, and for k equals 4, it will be this 4 square, and then if we take k as 5, again it will be 5 into 6, odd number, so it will be this minus 5 square. So essentially, this minus 1 to the power k plus 1 by 2, it will be minus 1 if k is of the form 4r plus 1 or 4r plus 2, and will be plus 1 if k is 4r plus 3 and 4r. So that means if we make them a pair of 4, then first two terms they'll have minus sign, and next two terms they'll have plus sign. So we can write this as minus 6 square plus 7 square plus 8 square, and we'll continue. So we'll have total 4n terms. So we'll have n such groupings. Now what we'll do is we'll take 1 and 3 together and 4 and 2 together. So we can write Sn. Now this is 3 square minus 1 square. So it'll be 3 minus 1, 2, and then 1 plus 3 plus 4 square minus 2 square. It'll be 4 minus 2, 2, and then 2 plus 4. In the same way, 7 square minus 5 square, 2 into 5 plus 7. This is 2 into 6 plus 8. It'll continue up to 2 into 4n. Now what we'll do is we can take 2 common. So it'll be this 1 plus 2 plus 3 plus 4 up to 4n, which is sum of first 4n terms. So it'll be equal to 2, and this is n plus 1 by 2. So this 2 and 2 will cancel. So this is 4n into 4n plus 1. So this Sn can take the value when we have two consecutive numbers such that one of them is a multiple of 4 and the other one leaves a remainder 1 when divided by 4. Now 1056, it is 11 into 6 into 4 into 4, which is 32 into 33, which satisfies this criteria. So this A, it is correct. Now what about 1088? 1088 is 16 into 4 into 17. Now this is 32 into 34, which is not possible. So option B is incorrect. Now option C is 1120, which is 16 into 7 into 10. So we'll take 4, and this is 4 into 7 to 5 into 2. So there is no possibility of making it of the form 4n, 4n plus 1. So C is incorrect and D is 1332. It will be 4 into 3 into 3 into 37. Now this is 36 into 37, and 36 is a multiple of 4. So the correct options are A and D. Now the question is we need to find sum of the series, which is 1 upon x plus 1 plus 2 upon x plus 1 square plus 2 square upon x to the power 4 plus 1 up to 2 to the power 100 upon x to the power 2 to the power 100 plus 1. Now here we see in the denominator we have x plus 1, x square plus 1, x to the power 4 plus 1. So I suspect it has something to do with x minus 1. So what we'll do is we'll add x minus 1 and we'll subtract x minus 1. So we can write this as 1 upon x minus 1 minus 1 upon x minus 1 plus 1 upon x plus 1 plus 2 upon x square plus 1 up to 2 to the power 100 upon x to the power 2 to the power 100 plus 1. Now we simplify this, we'll get this as 1 upon x minus 1, and here it will be x square minus 1. Here will be minus x minus 1 plus x minus 1. X will cancel, so it will be this minus 2 upon x square minus 1, and this is plus 2 x square plus 1 up to 2 to the power 100 x to the power 2 to the power 100 plus 1. Now this again is the same format. If we simplify this, we'll get this as minus 2 square upon x to the power 2 square minus 1, and it'll continue till the end. So in the end, we'll have this as 1 upon x minus 1 minus, and we'll have this as 2 to the power 101 upon x to the power 2 to the power 101 minus 1. Now we need to find this value when the value of x is 2. So if we put x as 2, we'll get this as 1 minus, and this is 2 to the power 101 upon, this is 2 to the power 2 to the power 101 minus 1. Now here the question is, we have defined nm as this product n minus m, n minus 2m to n minus km, where k is the greatest number such that n is greater than km. We need to find the value of 72.8 and 18.2. Now if we look at 72.8, it will be 72 minus 8, 72 minus 16, 24, and you go up to 72 minus 64, and here it will be 18 minus 2, 18 minus 4, and 18 minus 16. Now this is 72. 72 minus 8 is 64. 64 minus 8 is 56. And this is 8. This is 16. So we have all the numbers 8, 8 into 2, 8 into 3, up to 8 into 9. And here we have 2, 4, and this is 14, 16, and 18. Now here we'll take 8 common from each term. So altogether there are 9 terms. So it will be 8 to the power 9 into factorial 9, and here we'll take 2 common from each term. So it will be 2 to the power 9 factorial 9. Now factorial 9 and factorial 9 will cancel. It will be equal to 4 to the power 9, and that's your option A. Now here we have 2 questions. The first question is, we are given that summation r varies from 1 to infinite 1 upon 2r minus 1 whole square, it is equal to pi square by 8. Then we need to find sum of this series. R varies from 1 to infinite 1 upon r square. Now basically, if we put r as 1, this is sum of odd terms. So it is 1 upon 1 square, 1 upon 3 square, plus 1 upon 5 square, and we are given that it is equal to pi square by 8. And we need to find sum of the series, which is 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square plus 1 upon 4 square up to infinite. Now what we'll do is, we'll separate even and odd terms. So we can write this series as 1 upon 1 square plus 1 upon 3 square plus 1 upon 5 square, and then it will be 1 upon 2 square plus 1 upon 4 square plus 1 upon 6 square up to infinite. Now sum of this series, it is already given in the question, pi square by 8. So this sum, it is pi square by 8, and plus here we'll take 1 upon 2 square common. So we'll take 1 by 4 common, and then we'll have 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square up to infinite, and this is nothing but this is simply s. So it is s equals pi square by 8 plus s by 4, or we can write 3s by 4 equals pi square by 8, or value of this s is pi square by 6. So value of this sum, 1 upon 1 square plus 1 upon 2 square plus 1 upon 3 square up to infinite, it is pi square by 6. That is one of the very famous problem known as the Basel problem, and we have already made a video on how to prove 1 upon 1 square plus 1 upon 2 square is equal to pi square by 6. Now we are given the second question. In the second question, we are given that 1 upon 1 to the power 4 plus 1 upon 2 to the power 4, 1 upon 3 to the power 4 up to infinite, it is pi to the power 4 upon 90. We need to find sum of odd terms. Now here also we'll separate odd terms and even terms. Now suppose this series is S. We can write this S as 1 upon 1 to the power 4 plus 1 upon 3 to the power 4 plus 1 upon 2 to the power 4, 1 upon 4 to the power 4, and this is equal to pi to the power 4 upon 90. Now this is the required sum that we need. Suppose this is s dash, and here we'll take 1 by 16 common, and here will be 1 upon 1 to the power 4 plus 1 upon 2 to the power 4 up to infinite, that is pi to the power 4 upon 90. Now this is the given series, so this value, it is pi to the power 4 upon 90. So we can write s dash plus pi to the power 4 upon 90 into 1 by 16, it is equal to pi to the power 4 upon 90, or s dash is 15 by 16 pi to the power 4 upon 90. Now this is 6 times. So this s dash will be pi to the power 4, and this is pi to the power 4 upon 96. So sum of this odd series is pi to the power 4 upon 96, and that's your option A. Now in this question we are given this function fn, and this fn, it is 1 by 2 plus n by 100, where the square box, it represents greatest integer function of x. We need to find this value. Now we know that if n lies between 1 and 49, then 1 by 2 plus n by 100, it is less than 1. In that case, value of fn will be 0, and if n lies between 50 and 100, then 1 by 2 plus n by 100, it will be greater than or equal to 1, but less than 3 by 2. So in that case, value of fn will be equal to 1. Now if we look at this required summation, it will be this summation, n varies from 1 to 100 fn. Now we can break this summation as n varies from 1 to 49 fn plus summation n varies from 50 to 100 fn. Now from 1 to 49, this is 0, and from 50 to 100, it is 1. So it is nothing but this summation n varies from 50 to 100, 1, and this is nothing but 51, and that's your option B. A1, B unequal to 0, and for n greater than 1, we are given that an equals n upon a n minus 1. Then we need to find the value of a1 into a2 up to a10. Now basically this is product of two consecutive terms. We can write an into an minus 1, ab equal to n. Now if we put n as 2, we can write a2 into a1 will be simply 2. If we put n as 4, we'll write a4 into a3 will be equal to 4. In the same way, a6 into a5, this is 6. And in the end, we'll have a10 into a9 and will be equal to 10. We multiply all these terms, we'll get this product a1 into a2 into a3 up to a10, and there'll be 2 into 4 into 6 into 8 into 10, which is 2 to the power 5 into factorial 5. And that is 32 into 120, and which is 3840. So value of this product is 3840. Now here the question is, we are given that let a and be a sequence such that a1 plus a2 up to an, it is n square plus 3n upon n plus 1, n plus 2. It says if 28 into summation k varies from 1 to 10, 1 upon ak will be equal to p1 into p2 into pm, where p1, p2, pm are first m prime numbers. Then we need to find value of m. So we need to find how many primes are there in this prime factorization of this summation 1 by ak into 28. Now what we'll do is we'll write this as n square plus 3n plus 2 minus 2. So this n plus 1, n plus 2 will cancel. So we can write this as 1 minus 2 upon n plus 1 into n plus 2. Now using this result, we'll write the sum up to n minus 1 terms. So we'll replace n with n minus 1. So we can write a1 plus a2 up to an minus 1 will be 1 minus 2 upon, now it will be this n and n plus 1. Now if we subtract this second from first, everything will get cancelled. On the left hand side we'll get an, and it will be equal to minus 2 upon n plus 1 n plus 2 plus 2 upon n plus 1. Now here we'll take 2 upon n plus 1 common. So we'll have minus 1 upon n plus 2 plus 1 by n. So this an will be 4 upon n plus 1 n plus 2. So that's our an. Now if we look at 1 upon an, it will be n plus 1 n plus 2 by 4, and what we'll do is we'll multiply and divide it with 6. Now if we look at this result, this is n plus 2 n minus 1 n into 3 into 2 into 1. So basically this is n plus 2 c3. So we can write 1 by an will be equal to 3 by 2 into n plus 2 c3. Now we need to find this 28 into this summation k varies from 1 to 10, 1 by ak. So it will be 28 into this summation k varies from 1 to 10, 1 by ak. So it will be this 28 summation k varies from 1 to 10, 3 by 2 into k plus 2 c3. So it will be 14 into 3, and then this summation k varies from 1 to 10, k plus 2 c3. Now this is 42, and we can write this summation as 3c3 plus 4c3 plus 5c3 up to 12c3. Now 3c3 is 1. So what we'll do is we'll write this 3c3 as 4c4, which is also 1. Now here n is same, r differs by 1. So it'll be this 5c4. Then n is same, r differs by 1. So it'll be this 6c4. And we have solved this series in binomial. So it'll be this 42. And then it'll go up to 12 plus 1, 13 c4. Now this is basically 42 into 13 into 12 into 11 into 10 by 4, 3, 2 into 1. Now 12 will cancel. Now this is 21. So it'll be this 21 into 13 into 11 into 10. Now 21 is 7 into 3 and 10 is 2 into 5. So 7 into 3 into 13 into 11 into 2 into 5. So we can write this as 2 into 3 into 5 into 7 into 11 into 13. And here we can express them as product of 6 prime numbers. So in this case, value of m will be 6. And that is the answer to this question. Now here we are given two series. One of them is A, which is 1 square by 1 plus 2 square by 3 plus 3 square by 5 up to 1001 square by 2001. And then we have this B, which is 1 square by 3 plus 2 square by 5 up to 1001 square by 2003. First we need to find A minus B. Now if we write A minus B, we'll take these terms together. So it will be this 1 plus, and here will be this 2 square minus 1 square by 3, and then 3 square minus 2 square by 5, and here we'll have 1001 square minus 1000 square by 2001, and then minus 1001 square upon 2003. Now this is 1. This is A plus B into A minus B. So there will be 3 upon 3. This is 5 upon 5. And here it is 2001 upon 2001 minus 1001 square upon 2003. So each of this term, it is equal to 1. So this is 1 plus 1 plus 1, 1001 times. So we can write A minus B as 1001 minus 1001 square upon 2003. Now we can take 1001 common, and it will be 2003 minus 1001 divided by 2003. Now this value, it is equal to 500.7498. Now option C is A minus B is 500.74. Now can we take it as 0.74 or not? It is little dicey. So we are going to leave it open-ended. Definitely it is not 500.94. Now its greatest near function is 500. Now integer closest to A minus B is 501. So the correct options are A and B. This C, it is also incorrect. Even if we round off, it will be 0.75, not 0.74. Now here we are given a sequence of real numbers such that an plus 1 equals an plus under root of 1 plus an square and a0 equals 0. If limit n tends to infinite, an upon 2 to the power n minus 1 is k by pi, we need to find the value of k. Now, if we put n as 0, we'll get a1, and this a1 will be a0 plus under root of 1 plus 0, which is 1. Now we can write this one as cot pi by 4, or basically we can write this as sum cot theta, where theta is pi by 4. So this A2, it will be cot theta and plus 1 plus cot square theta is cosec theta. So there will be cot theta plus cosec theta, and this is 1 plus cos theta by sin theta, and it is cot theta by 2. If we substitute here cot theta by 2, we'll get cot theta by 2 square. So A3 will be cot theta by 2 square. So we'll get AN as cot theta upon 2 to the power of n minus 1, where theta is pi by 4. Now if we find this limit, which is limit n tends to infinite, an upon 2 to the power of n minus 1 will be this limit n tends to infinite cot theta upon 2 to the power of n minus 1 upon 2 to the power of n minus 1. We'll multiply it with theta and divide it with theta. So we can write this as limit n tends to infinite theta upon 2 to the power n minus 1 upon tan theta upon 2 to the power of n minus 1 into 1 by theta. Now when n tends to infinite, 1 upon 2 to the power n minus 1 tends to 0. So it is 0 upon 0 form. So now this is standard limit x upon tan x, which is 1. So value of this limit is simply 1 by theta, which is 4 upon pi. We are given that this limit is equal to k upon pi. So value of k in this is simply 4, and that is the answer to this question. Now here the questions. We are given the series Sn, which is 1 plus 1 by 2 plus 1 by 3 up to 1 by n. We need to find this value S1 plus S2 up to Sn minus 1. Now what we'll do is, rather than finding the sum, we'll find the sum of S1 plus S2 up to Sn, thereby getting a better symmetry rather than taking n minus 1. So we can write this as 1 plus 1 plus 1 by 2, 1 plus 1 by 2 plus 1 by 3, and we'll continue up to 1 plus 1 by 2 plus 1 by 3 up to 1 by n. We have this one n times, so we can write this as n upon 1, and then we'll have n minus 1 by 2, n minus 2 by 3, and in the end we'll have n minus 1 by n. Now what we'll do is, we'll take these terms of n together and we take n common. So it'll be 1 plus 1 by 2 plus 1 by 3 up to 1 by n, and then we'll have minus 1 by 2, minus 2 by 3, minus 3 by 4 up to minus n minus 1 by n. And what we'll do is, we'll add 1 to each term, and we have added this 1 n minus 1 times. So we'll write minus n minus 1. So we'll get the series as S1 plus S2 plus Sn minus 1 plus Sn. It will be n into Sn. Now this is plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by n, and we'll add 1 and we'll subtract 1. So this again will be Sn, and here will be simply minus n. This Sn and Sn will cancel. So sum of the series S1 plus S2 up to Sn minus 1 will be simply Nsn minus n. And that's your option A. Now it should be R here. R varies from 1 to n. R to the power 4, it is equal to Fn. That means 1 to the power 4 plus 2 to the power 4 plus 3 to the power 4 up to n to the power 4 is fn. We need to find this sum. Summation r varies from 1 to n 2r minus 1 to the power 4. So we need to find 1 to the power 4 plus 3 to the power 4 plus 5 to the power 4 to 2n minus 1 to the power 4. So what we'll do is, we'll start with f2n, and f2n will be 1 to the power 4 plus 2 to the power 4 plus 3 to the power 4 up to 2n to the power 4. Now here again we separate even and odd terms. So we write odd terms together, 1 to the power 4 plus 3 to the power 4 and plus we'll have 2 to the power 4 plus 4 to the power 4 up to 2n to the power 4. Now this is the required summation that we need. So we can write f2n and ab equal to this summation r varies from 1 to n 2r minus 1 to the power 4, and here we'll take 2 to the power 4 common, so it will be the 16, and then 1 to the power 4 plus 2 to the power 4 up to n to the power 4, which is nothing but fn. So this is fn. So from here we can say this summation r varies from 1 to n 2r minus 1 to the power 4 will be equal to f2n minus 16fn for all n. So the correct option is this option A. Now here the question is, let TR be the rth term of an AP whose first term is minus 1 by 2. So first term is minus 1 by 2 and common difference is 1. Now its rth term will be A plus r minus 1 into d, which is r minus 3 by 2, or we can write simply 2r minus 3 by 2. Now tr plus 1th term will be 2r minus 1 by 2. tr plus 2th term will be 2r plus 1 by 2, and tr plus 3rd term will be 2r plus 3 by 2. Now it says we need to find this series, which is summation r varies from 1 to n under root of 1 plus tr plus 1, tr plus 2, and tr plus 3. That will be this summation r varies from 1 to n, and this is under root of 1 plus, and this is 2r minus 3 into 2r minus 1, 2r plus 1, 2r plus 3 upon 16. Now this is a plus b into a minus b. So we can write this sum as this summation r varies from 1 to n, and it will be this under root of 1 plus, and this is 4r square minus 1 into 4r square minus 9 whole divided by 16. Now we take 1 by 4 common, and it will be this summation r varies from 1 to n, and here it will be this 16 plus 16r to the power 4 minus 10 into 4r square plus 9. Now this is 1 by 4 summation r varies from 1 to n, and it will be this 4r square whole square minus 10 into 4r square plus 25. So this is a square plus b square minus 2ab, and which is a minus b whole square. So it will be this 1 by 4, and then summation r varies from 1 to n 4r square minus 5. Now this sum will be 1 by 4 and 4r square is n plus 1, 2n plus 1 whole divided by 6, and minus 5n. So this sum, it will be n plus 1, 2n plus 1 by 6, and minus 5n by 4. And that's your option A. Now here we given that consider a sequence of natural numbers S0, S1, S2 such that S0 is 3, S1 is 3, and Sn is 3 plus Sn minus 1 into Sn minus 2. Then which of the following is or are correct? Now if we look at this series, we know S0 is odd, S1 is odd. Now if we look at S2, S2 will be 3 plus 3 into 3. Now this is odd plus odd, so it will be even. So we'll have S2 and this S2 will be even. Now S3 is odd plus S1 into S2, so it will be odd into even, and odd into even is even, and odd plus even is odd. So we'll have S3 odd. Now S4 will be 3, which is odd, plus S2 into S3. So this is even into odd, which again is even, and plus odd. So this again is odd. So S4 will be odd. Now S5 will be odd plus odd into odd, and there will be even. So this is even. So we'll get even if and only if previous two terms they are odd. We'll have this series where S2 is even, S5 is even. So basically S3n plus 2, it is even, and if it is a multiple of 3 or it is of the form 3n plus 1, then it will be an odd number. Now it is asking for S1545 and S1546. Now if we look at 1545, it is divisible by 3. So this is 3 into 5, 1, 5. So it's a multiple of 3. So it is of the form 3n. So this is odd. And 1546 will be 3 into 515 plus 1, which is of the form is 3n plus 1, which also is odd. So both these numbers, they are odd. That means the correct option is this. Now the question is, we need to find sum of the series, which is 1 upon x plus 1 plus 2 upon x plus 1 square plus 2 square upon x to the power 4 plus 1 up to 2 to the power 100 upon x to the power 100 plus 1. Now here we see in the denominator we have x plus 1, x square plus 1, x to the power 4 plus 1. So I suspect it has something to do with x minus 1. So what we'll do is, we'll add x minus 1 and we'll subtract x minus 1. So we can write this as 1 upon x minus 1 minus 1 upon x minus 1 plus 1 upon x plus 1 plus 2 upon x square plus 1 up to 2 to the power 100 upon x to the power 2 to the power 100 plus 1. Now we simplify this, we'll get this as 1 upon x minus 1, and here will be x square minus 1. Here will be minus x minus 1 plus x minus 1. X will cancel, so it will be this minus 2 upon x square minus 1, and this is plus 2 x square plus 1 up to 2 to the power 100 x to the power 2 to the power 100 plus 1. Now this again is the same format. If we simplify this, we'll get this as minus 2 square upon x to the power 2 square minus 1, and it'll continue till the end. So in the end, we'll have this as 1 upon x minus 1 minus, and we'll have this as 2 to the power 101 upon x to the power 2 to the power 101 minus 1. Now we need to find this value when the value of x is 2. So if we put x as 2, we'll get this as 1 minus, and this is 2 to the power 101 upon, this is 2 to the power 101 minus 1. Now in this question, we are given that for triangle ABC, 81 plus 144 a to the power 4 plus 16 b to the power 4 plus 9 c to the power 4, it is equal to 144 ABC. Then which of the following is correct? So what we'll do is we'll consider these four numbers and we'll write their arithmetic mean, and it'll be 81 plus 144 a to the power 4 plus 16 b to the power 4 plus 9 c to the power 4 upon 4, and it will be greater than or equal to their geometric mean, which is 81 into 144 a to the power 4 into 16 b to the power 4 into 9 c to the power 4 whole to the power 1 by 4. Now we simplify this. This is 144 is 12 into 12. So there will be 9 into 16. Now this is equal to 4 to the power 4, 9 to the power 4, a to the power 4, b to the power 4, c to the power 4 to the power 1 by 4. So from here we can write 81 plus 144 a to the power 4 plus 16 b to the power 4 plus 9 c to the power 4 upon 4 will be greater than or equal to 36 ABC, or we can write 81 plus 144 a to the power 4 plus 16 b to the power 4 plus 9 c to the power 4, it is greater than or equal to 144 ABC. But in the question we are given that there is an equality sign, and we know that AM is only equal to GM if and only if all the numbers are equal. That means 81 must be equal to 144 a to the power 4, and it is equal to 16 b to the power 4, that is equal to 9 c to the power 4. So from here we can write this as a to the power 4 equals 9 by 16, b to the power 4 equals 81 by 16, and c to the power 4 equals 9. So from here we'll get a as root 3 by 2, b as 3 by 2, and c as root 3. Now this clearly we can see that a is less than b and is less than c. So sine a will be less than sine b and it will be less than sine c. And since sine is an increasing function and all these values, they are positive, so it will lie in the first quadrant. So angle A will be less than angle B and will be less than angle C. So that means option A is incorrect and option B is correct. Now if we look at A square plus B square, there will be 3 by 4 plus 9 by 4. Now this is 12 by 4, 3, and which is C square. That means triangle ABC is a right angle triangle. So option D is also correct. So this triangle ABC, it is a right angle triangle and these sides are AB and hypotenuse is C. Now area of this triangle will be half AB and this value is going to be 1 by 2. A is root 3 by 2 and B is 3 by 2. So this value is 3 root 3 divided by 8 and that's your option C. So the correct options are B, C and D. Now here the question is, we are given a number which is of the form 7, 5, 5, 5, 7, and here we have total are 5s, and then we have these two numbers 7. So basically it is r plus 2 digit number. So first and last digit are 7 and remaining digits are 5. So consider the sum as, which is 77 plus 757 plus 7557, and goes all the way up to 75557, and here we are taking them 98 times. So basically it's a 100-digit number. Now it says we have to express this sum as 7 and then 99 times 5, 7 plus m by n, where m and n are natural numbers less than 3000. Find the value of m plus n. So somehow we have to solve this series. Now generally when I see this pattern, I know we have to use difference somewhere. So what we'll do is we'll write 10s. So we'll multiply this series with 10 and we'll shift the series by 1 unit. So here it will be 770. Here it will be 7570. And this term here will be 755570. So here we have 98 5s and then we have 70. Now what we'll do is we'll subtract first from second. So if we subtract first from second, now 10s minus s is basically 9s. Now this is minus 77. Now 770 minus 757. Essentially this is 70 minus 57. So it will be this 13. Now here also 75. It's of no use. 70 minus 57 is again 13. I'll continue up to this term, which is 13 plus this 7, 555, 98 times, and then this is 70. Now first thing is, how many 13s do we have? So we have started with 1 and we have gone up to 98 5s. So this 13, it appeared 98 times. So we can write this 9s will be minus 77 plus 13 into 98 plus, now here we need 7, 5, 5, 5, 5, 5, 7, 99 times. So what we'll do is we will subtract 13 and we'll add 13. So here we'll add 13, and if we subtract 13, it'll become 7, 5, 5, 5, 5, 7, and now this is 99 times 5. So basically this is 9s and this is 13 into 99 minus 77 plus 7, 5, 5, 5, 7, 99 times, which we need in the question. So it will be 1210 plus 7, 5, 5, 5, 5, 99 times 7, or we can write this as 1210 plus 7, 5, 5, 5, 5, 99 times 7 whole divided by 9. Now we have put it in this form. Now this is your m and that's your n. We need to find the value of m plus n. So value of m plus n is 1210 plus 9. So there will be 1219, and that is the answer to this question. Now here the question is, prove that
A triangle ABC is equilateral if and only if tan A plus tan B plus tan C equals 3 root 3. So it is if and only if. So we have to prove it both ways. So first is let ABC be equilateral. So let triangle ABC be equilateral. In that case, A equals B equals C equals 60, and in that case tan A will be equal to tan B will be equal to tan C, and they'll be equal to root 3, and therefore tan A plus tan B plus tan C is 3 root 3. Now we prove the second part, that let tan A plus tan B plus tan C, it is equal to 3 root 3. Now we need to prove that this triangle is an equilateral triangle. Now we know that in a triangle tan A plus tan B plus tan C, it is equal to tan A into tan B into tan C. If we use AM and GM, then we can write tan A plus tan B plus tan C by 3 will be greater than or equal to tan A into tan B into tan C to the power 1 by 3. Now suppose this is x. So we can write x by 3 is greater than or equal to x to the power 1 by 3, or we can write x to the power 2 by 3 will be greater than or equal to 3. So from here we can write x is greater than or equal to 3 root 3. So for any triangle, this tan A plus tan B plus tan C will always be greater than or equal to 3 root 3. Now in this question we are given this equality, and we'll have this equality if and only if all the three numbers they are same. That means tan A should be equals to tan B and it should be equal to tan C. So from here we'll get A equals B equals C, and therefore this triangle ABC is equilateral. Now the one question that pops up in the head is, how can we use AM and GM if we do not know whether these three numbers they are positive? But we know that tan A into tan B into tan C is 3 root 3, which is a positive number. That means all the three angles A, B and C, they'll be acute. And that's the reason we have used AM and GM in this question.